So before we start with the problem, it's important that we understand and know the new variables, new constants on our formula sheets, and our new formulas, of course. So I'm just going to go over some of the newer stuff. Maybe you guys would have trouble with and not really recognize initially. Let's do omega. So that's going to be this fancy W looking thing. Omega represents our angular velocity. So angular velocity is going to be omega. And our units for omega are radians per second. So radians per second. So omega, radians per second. Omega is an analog to the tangential velocity that we've been working with. So yeah, it's just angular velocity. Next, let's look at theta. We've known theta to mean just an angle. It's essentially the same. It's going to be angular displacement. So angular displacement. So theta is our angular displacement. Our units we're going to use are radians. So theta, angular displacement, our units are radians. And theta is an analog, theta is an analog to our tangential displacement that we've been using initially. We also have alpha, so it's going to be fancy looking A. You can probably guess what that is. It's going to be our angular acceleration. You can probably also guess what the units would be, and that's going to be radians per second squared. So those are essentially the big three. We could also throw in R, which you would probably guess what that is. That's going to be our radius. So that's pretty simple. No units there. Oh, I guess actually the unit of meters is going to be a measure of length. Oh, that's right. The M out there. So R is going to be our radius. And then one more that I think you guys might not be able to get too early on is going to be the capital T. So you've never seen this, the big capital T. The big capital T is going to be your period. So if you ever see anything where you want to solve for the period, that's it. Period is going to be like one full rotation or follow the path one full time. So if a satellite goes around the Earth one time, it's completed one period. So, or the time it takes rather is the period. So how about that? Period is going to be a measure of time. So unit's going to be seconds. So you've got omega, you've got theta, you've got alpha, you've got R for radius, and you've got T, capital T rather, for period. So those are the new ones. If you got those, you're probably good for this first part of the new section. And yeah, that's it. Let's move on. Alright, so the first one we're going to look at, we've got a centrifuge in a medical laboratory. It rotates at an angular speed of 4,000 revolutions per minute. When switched off, it rotates through 40 revolutions before coming to rest. And we want to find the constant angular acceleration of the centrifuge. So we've got a few values. We know our initial angular velocity, or omega, is going to be 4,000 revolutions per minute. So omega is 4,000 revolutions per minute. We know that's going to be switched off and go through 40 revolutions. So our theta is going to be 40 revolutions. We also know that it's going to come to rest. So final angular velocity is going to be 0. And we're going to do omega final equals 0. We want to find the constant angular velocity of this system. So we're going to do alpha equals, I'm just going to put a question mark. So that's what I'm looking at. Should have something similar to that. That's just what we have given to us. So we need to convert these to standard units. The 4,000 revolutions per minute is going to go from 4,000. We're going to multiply 1 revolution is 2 pi radians, so by 2 pi, and then minutes, 1 minute is 60 seconds, so minutes, seconds, 1 minute, 60 seconds. So that's the calculation. See if you got that. So we're gonna do 4,000 times 2 pi over 60. I'm getting 418 radians per second. If you got something different, pause the video and redo it. So we got 418. I'm going to do 0.89 radians per second. We've also got to convert theta, or our 40 revolutions, to radians. So we're going to do 40 times 2 pi to get that in radians. So we're going to do 40 times 2 pi would be 80 pi. So let's just do that. Calculator. I'm getting 251.327 radians. So I'm gonna write that on my board as well. So 251.33 radians, right? We've already got our final angular velocity is 0. We can convert that, but it's going to be 0 as well, so we can just put 0 radians per second. Easy. And you want to find alpha, so take a second, look over your formula sheet, pause if you need to, and we're going to use W, or omega final squared, equals omega initial squared plus 2 times alpha times the change in delta. So that's what I'm looking at. That formula right there. So you can plug in our values. 0 squared equals 418.89 squared plus 2 times alpha, which we don't know, times the change in our radians. That's going to be 251.33. So that is our numbers put in there. And let's do a little algebra. So we got this. Pause the video if you hadn't got the value yet. Finish your calculations up. I'm getting angular acceleration as negative 349.1 radians per second squared. So if you got anything different, I don't know, look at your math again, but I'm getting negative 349.1. So the next one we're going to look at, we've got a rotating wheel, requires 10 seconds to rotate 33 revolutions. Its angular velocity at the end of the 10-second interval, it's 100 radians per second. We want to know what is the constant angular acceleration of the wheel. So let's look at that. They tell us that we've got a 10-second time interval, so go ahead, write down what variable that is and your value. We're going to rotate 33 revolutions, so you can write your variable. You should know it. 33 revolutions. This one I'm going to ask you. Take a second. If you don't know it, look at your notes, but you should have theta equals 33 revolutions. We also have a final angular velocity of 100 radians per second. So our final angular velocity is going to be 100 radians per second. So we're going to do that variable final equals 100 radians per second. It's going to ask you what that variable is. You don't know it, look at your notes, make sure you got it, but it will be omega final. So we've got that, and we want to know what our constant angular acceleration is. So we want to know our constant angular acceleration. So that variable equals, and we don't know, so I'm going to throw a question mark. Get your variables straight, make sure you know how to do those, but this is what I have. Time, 10 seconds, theta, 33 revolutions. Omega final, 100 radians per second. Alpha equals unknown. So we don't know alpha yet. We've got all this. We want to know alpha. We realize we don't know our omega initial either, so we can go ahead and throw that up there potentially. And look at your formula sheet, see what you can use to find anything. I don't believe you could find alpha so easily. So let's find omega first. So take the time, pause, look at your formula sheet, see what you want to use to find omega initial. So take your time. I'm going to use change in omega, delta omega equals 1/2, or actually change in theta equals 1/2 omega initial plus omega final times time. So if you found this, good job. And potentially you could have used something else, but this is the way I'm going to do it. So we've got that. Theta, we actually have to convert that to radians. So maybe you've already done that, but take the time to convert that to radians. You should have gotten 66 pi radians. If you didn't, pause, look at the math again, but that should be your theta here. So we've got 66 pi equals 1/2 omega initial, which we don't know, plus omega final, which is the 100 radians per second, times time, which is 10 seconds. So this is what I'm looking at. That is my work. I'm going to do the math and solve for omega initial. So let's try it. Pause, make sure you've got your value first, but I'm getting negative 58.53 radians per second. So you should have gotten negative 58.53 radians per second for your initial omega, your initial angular velocity. So we've got initial angular velocity of negative 58.53 radians per second. So now we've got that, we can find what we really want to find, the alpha or angular acceleration. So look through your formula sheet, your notes, determine what variable you want to use or formula you want to use rather, and pause if you can't find it, but we're going to use omega final squared equals omega initial squared plus 2 alpha times the change in theta. We're going to plug in our values. We're going to use 100 for our final velocity. We're going to use negative 58.53, which we just found, for our initial velocity, plus 2 times alpha, which we don't know yet, times change in theta, which we know is the 66 pi. So clean up a little bit, but you've got the gist. this is what I'm looking at right here. So we've got that. We can do a little math, and that should be it. So minus 58.53 squared divided by 2, and then divided by 66.5. I got 15.85 radians per second squared as my final angular acceleration. Let's see, or a constant angular acceleration. That should be the answer. If it's not, or if that's not what you got, redo it, look at your math again, but we've got 15.85 radians per second squared. With the last two problems, we looked at more of the angular motion, angular kinematics type stuff. That should be easy for you guys. Let's focus on some of the tougher stuff in chapter 7 now. Number 3, we've got an adventurous archaeologist, mass 90 kilograms, tries to cross river by swinging from a vine. The vine is 12 meters long, and the speed at the bottom of the swing is 8 meters per second. The archaeologist doesn't know that the vine has a breaking strength of 1,200 newtons. Does he make it safely across the river without falling in? And the answer would just be a yes or no. But we've got to do math there. So let's look at it. So what we're given is the mass, 90 kilograms. So we can write that. M equals 90 kilograms. We also know the vine is 12 meters long. Take a second to think about what you think that would be. If you thought to yourself that would be the radius, you're right, you're on the right track. So 12 meters is our radius here, and the speed at the bottom of the swing is 8 meters per second. We've got meters per second, so we know that that is just going to be the regular old velocity we've been using. So you can write that variable down there, 8 meters per second. And a little side note we know is that the breaking strength of the vine is 1,200 newtons. So let's say that force max equals 1,200 newtons. How about that? So this is what I have. You should have something similar. Those are all of our variables. I also like to draw these, help us out a little bit. So let's take a second to draw a little picture. So we can draw a little force diagram with it, right? So we can do the man with his vine. We can draw our forces acting. And you should have two forces acting, right? So consider that, and also consider the path of the swinging vine, right? What would that look like? How would that affect your problem solving here, right? So almost done my picture, you should be as well. If not, pause, take a second to get this right. What I've got is poorly drawn as it is. The man, his vine, tension going up, weight pulling down. We know the vine is a length of 12 meters, and he's gonna go through like a little circular path there. So that's what we're dealing with. And if that's the case, we could use a little formula or idea or concept that we've used previously. Consider that for a second. Pause if you need to. But we're going to work with Newton's second law a little bit. So that was on your last section. You should be familiar with it. But we know that sum of the forces equals mass times acceleration, right? Make sure you know your Newton's second law. You're going to keep using it. So we've got that. we want to look at the sum of our forces. There should be two of them. So take a second to determine what they are. If you said we had tension going up and weight pulling down, you'd be exactly right. We've got mass times acceleration here, but you should consider that we're going in a circular path, right? So we're going to use centripetal acceleration, right? So we're going to use alpha here. The idea here is that we have a velocity, we have a radius, we know we could find centripetal acceleration with those values. So we're going to replace the A, or alpha rather, with a v squared over r. Since centripetal acceleration always points to the center of the circle, we're going to just make it positive. So we've got tension minus weight equals mass times v squared over r. Pretty straightforward. Relook at your notes, look at Espino's video, look at Daniel's video. If you've not got that, make sure you've got that, because that is very critical to your success this next exam. So I'm gonna erase a little bit. We know that we don't have the tension just yet, so we're gonna say tension equals, right? We're just gonna move over the mg. We're gonna say mg, which is 90 times 8, or actually 90 times 9.8 rather. We're going to add that to the mv squared over r. So we're going to do 90 times v squared over r. So it's going to be the 8 squared over the r, which is 12. So this is the last bit of work. If you've got that, you're good. If not, work on it. But let's just do the math really quickly. So we've got, what we should have rather, I'm getting a tension of 1,362 newtons. Got that good? If not, pause, look at it again, make sure you get it right. So if that's the case, he's got a tension of 13,000, or actually 1,300, and the max that the rope can withstand is 1,200. He obviously does not make it across here, so we're gonna put a no there as our answer. Big old no. No, does not make it. And that's it. So there you go. The next problem we're going to look at is the air poke problem. Mass 0.15 kilograms tied to a string allowed to revolve in a circle of radius r equals 0.75 meters on a frictionless horizontal table. The other end of the string passes through a hole in the center of the table, and mass of 1.5 kilograms is tied to it. The suspended mass remains in equilibrium while the puck on the tabletop revolves. First, we want to know what is the tension in the hanging string. So before we even do that, let's draw a little picture. It helps to always be able to visualize these. So let's take a second to draw what we're looking at. And you should be familiar with this one because it is similar to a homework problem you will have. So we've got that little string, circular path. Now I've got something like this. Little table, puck going around. Maybe I could have used a different color. We've got a weight hanging down as well. We need to add in our values. We know that the puck on the table is 0.15 kilograms. The puck hanging is going to be 1.5 kilograms. So 10 times heavier. We've also got a radius of that string, which is 0.75 meters, or radius of that path. So let's do that, 0.75 meters. And And we know the suspended mass remains in equilibrium while the puck on the tabletop revolves. So that's going to help us. So I've got all this good information. So take a second to think about what we're going to use and actually tell me if you know. But if you said Newton's second law, you're exactly right. So we're going to use sum of our forces equals mass times acceleration. You should be familiar with that one. So let's look at these as two different bodies, similar to how we would approach what Atwood's machine problem. So this is similar to an Atwood's machine problem. So let's focus on the reddish mass first, right? So it's an equilibrium. Let's do a Newton's second law problem for that, or equation for that. So take your time, write out what you have. If you don't have it yet, pause, but you should have rather, tension minus weight equals 0. So you've got the tension going up, you've got weight pulling down, and they're hanging in equilibrium, so they're canceling each other out. Tension is going to be, we don't know it yet. So you can say tension equals, we move the weight over, we're going to use mass 1.5 times 9.8. That's what we're dealing with. A little math. Shouldn't take you long at all. If you're getting 14.7, you're good. Let's move on. If not, let's not. But yeah, I believe part A just wanted the tension. So that is it, the 14.7. And your variable, or actually your units rather, would be newtons. Part B wants to know what is the horizontal force acting on the puck or the tension on the string. That's also going to be the 14.7. It's going to be an Atwood's machine type problem. So 14.7 down, 14.7 rotating around. And lastly, you want to know what is the speed of the puck. So think about your approach there. Actually, let me erase the picture, but it doesn't matter. Table, puck going around. We've got our radius as, let's see, our radius was 0.75. And the relevant mass there was 0.15 kilograms. So we know all that. So similar approach, we're going to do Newton's second law. Sum of the forces equals mass times acceleration. Our forces here, only relevant force is going to be the tension. And that should be causing the angular rotation, right? So we've got mass times angular acceleration, which would be, we're going to use v squared over r. So that's what I'm looking at here. Tension equals mass times v squared over r. And that is because the tension is what's causing the angular rotation here. We can plug in our values. We know tension is 14.7. We just found that a second ago. Mass is going to be 0.15 here for the puck on the table. Velocity is what we're looking for, so we're going to just put the v squared there. R we know is radius, and that's going to be the 0.75 meters. So we've got that. This is my last little bit of work, and let's get a value there. So do a little math. And I'm getting a final answer of velocity equals 8.57 meters per second. So that's what you should have gotten. If not, look at it again, re-look at it, look at every step, because that is the right answer. Make sure you can do this problem. It is going to be seen again, I assume. So number 5, we've got the roller coaster problem. We've got a roller coaster, 600 kilograms. And for part A, we want to know if the vehicle has a speed of 20 meters per second. What is the force of the track on the vehicle at this point? So what are we looking for here? Say it out loud. We're looking for the normal force, right? And let's actually draw this picture. So we've got point A and point B. And point A is in a circular valley. Point B is at the peak of a circular path as well. And we've got a radius of point B at 15, and we've got a radius of point A at 10. So of course we're looking at this pretty picture. We know that speed at point A is going to be 20 meters per second. We also know our mass is going to be the 600 kilograms. We've got all that. Part A, we want to find normal force, right? So we're going to use the concept we've been using, and you should be familiar with it by now. Let's say it out loud. We know we're looking for Newton's second law. Sum of the forces equals mass times acceleration, right? So here's what I've got so far. Nothing much, but the picture, sum of force equals mass times acceleration, and our values. So let's look at our forces, right? We've got, if we're on the track, we've got normal force pushing up, we've got weight pulling down, right? So we could say normal force positive minus the weight, which is going down, right, equals mass times acceleration. We're following a circular path, right? So we're going to use circular acceleration here. So instead of A, we're going to plug in our handy dandy v squared over r. I'm sure you're wondering why I keep using the v squared over r. It should be on your formula sheet, but angular acceleration could also be stated as v squared over r. So that's the case there. So I wrote that out, and this is what I'm looking at. You want to solve for normal force, so let's just rearrange it and put our values in at the same time. So I'm going to rearrange a little bit. Normal force equals the weight, which is going to be the 600 times 9.8. And we're going to add that to the mass times the velocity over the radius. Velocity squared over the radius. So that's 600 times 20 squared over 10, right? So that's what I'm looking at there. That right there. Do a little math here. Shouldn't be too tough. 600 times 9.8 plus 600 times 20 squared over 10. And our normal force should be a value that you found. Erase a little bit just to write it on the board. I'm getting 29,880 newtons. If you've not got that, do it again, pause, make sure you get that first step right. That is the more simple step. You should be able to do that, and if not, just run through the notes again. So we've got that. Let's leave our picture. Part B, we want to find what is the maximum speed the vehicle can have at point B in order for gravity to hold it on the track. So as long as the car is on the track, or the roller coaster vehicle is on the track, it's going to have a normal force. As it leaves the track, it approaches zero. The normal force will approach zero. So the idea here is that if it's off the track, normal force is going to be zero. So here we're just going to say normal force is 0, and we're going to solve it the exact same way. So Newton's second law, right? Should be able to say that by memory. Fundamental forces equals a mass times acceleration. We've got, again, two forces. You should know what they are, so I'm not going to say them. Equals mass times centripetal acceleration. So mass times v squared over r. So this is what I've got. If you've not got that, look at it again, because that is it. So we've just used Newton's second law. We've used centripetal acceleration. We're going to plug in our values now. So I don't know why I wrote tension. It should be normal force. So normal force minus weight equals mass times centripetal acceleration over radius. I'm sorry for that mistake. So normal force we just said is going to be 0 here because it's approaching or it's leaving the track. So there would be no force of the track on the vehicle, right? Going to do 0 minus the weight, which would be 600 times 9.8. Maybe I could have left that as rearranged first, but it doesn't matter. Actually, it doesn't matter at all. It doesn't work out very well. An idea here, maybe you've already picked up on it. We're at the peak of a circular path, right? And centripetal acceleration always points towards the center of that circle. So we're at the peak, right? And the center is right here. We're going to have to go down for our centripetal acceleration, right? So we're going to say negative mass times velocity squared over r. So here's what I have. I'm going to plug in the values like we've been doing, and that would give us our final answer. So mass we know is 600. Velocity is going to be the 20. Radius is going to be 15 here, right? Do a little math here, and we should be able to get our final answer. The negatives on both sides should cancel out. So it should be pretty straightforward. We got 600 times 9.8. We're gonna, Oh, we're looking for the velocity rather. So I made a mistake earlier, but we should be looking for the velocity. So we divide by 600, multiply by 15, screw rid of that whole answer. I'm getting 12.1 meters per second. So we've got our final velocity as 12.1. Well, that was a little messy, but the concept should be with you. You should be able to do this by yourself. Velocity is 12.1. If you're at home catching these mistakes, good on you. Really good stuff. But yeah, not too tough. So for this problem, we're going to look at the satellite out in orbit. It's always good to draw these first. So let's see. I've already sort of gotten a head start on this one. So this is what we're looking at. We've got Earth, got the radius of Earth. The satellite is out another radius of Earth. So we've got essentially 2 times Earth radius as our functional radius. We know Earth's mass, and we also know the mass of the satellite is going to be the 700 kilograms. We want to find exactly what the velocity of the satellite would be as it's in Earth's orbit. So consider this. What is the force that keeps the satellite in Earth's orbit? And that would be gravity, right? So we want to find the force of gravity here. So we're going to use Newton's law of gravitation. Force equals gravity constant times mass 1 times mass 2 over r squared, right? Let's say mass 1 is Earth. We're going to put subscript E. And let's say mass 2 is the satellites. Let's do a little M. So far, that's what I have as far as work. And we know that's the force that holds the satellite in Earth's orbit. But what is the force that causes the circular orbit? It'd be the exact same force, right? So we could say that that force is also equal to mass times centrifugal acceleration, and we can replace the A for acceleration with a V squared over R. So in one step, here it is. So we've got the gravitation law equals mv squared over R. So the little m's are going to cancel out. We've also got an R at the bottom of both sides, so we can take out one R from both sides. So we're left with big G times the mass of Earth over the radius equals the velocity squared. Let's clean this up. We just plug in our values. So big G is going to be 6.67 times 10 to the negative 11. Earth's mass we know is the 5.98 times 10 to the 24 over 2 times 6.38 times 10 to the 6 equals velocity squared. And from there it's just algebra. So let's get our value. Take your time to calculate. Always make sure you're getting the right value out of your calculator. So be very careful with what you put in. So you should have gotten a value for velocity positive if you hadn't gotten one yet. And I'm getting 5,590.99 meters per second. Got anything different? Just take your time, pause, look over it again, but that is what you should have gotten, 5,590.99 or something in that ballpark. You may have rounded a little bit, but generally it should be fine. So we're going to erase that. And we now know that our velocity is 5,590. Part B, we want to know, we want to know what is the period of this revolution. So you should know by now that for the period we're going to use a variable what? T. Capital T is our variable for the period. So we want to know the period of our orbit. There's only one formula on your formula sheet that uses the period, or the capital T rather, and that's going to be Kepler's third law. So you should be able to go straight to that when you see any problem that wants to know what your period is, at least for now. So we've got period squared equals 4 pi squared over big G times mass of the body causing the gravity, or the orbit. So that's going to be the mass of Earth here. I'm going to use the radius times radius cubed. So it should be exactly what's on your formula sheet. I wrote it right here. Period squared equals 4 pi squared over big G times big M times R cubed, or the radius cubed. So plug in our values, pretty straightforward from here. Big G, of course, is going to be 6.67 times 10 to the negative 11. Big M is given to us as well, 5.98 times 10 to the 24th. Times R cubed, which is going to be our value here. I'm just going to plug it in. I don't have much space. And that is going to be our T squared, but let's just take the square root of that. And in one big ugly step, that's what we're looking at. But you got the idea. 4 pi squared over big G times big M times the radius cubed. We're going to take the square root of all of that. So not the most complicated as far as procedure. Just know what you're doing. Let's do a little math here, get our exact value. So let's get 1 second for that. And for our period, let's double check this. I'm getting 14,339 seconds. So 14,000, you can't really see that. 14,339 seconds. That should be your right answer. You followed the procedure exactly correctly. So we're gonna go with 14,339 seconds. Let's write that down. So we are running through this 14,339 seconds. Wrote that on the board. Part C, we want to find the gravitational force acting on the satellite. And we've already touched on that a little bit. We're going to use, again, Newton's law of gravitation, right? So force equals big G times big M times little m over R squared. Big M is going to be Earth. Little m is going to be the mass of the satellite. We know what big G is, and R squared is going to be the radius we have squared. So let's just move a little bit around. We're just going to plug those values in. So without me doing any real work, that is what we're going to do. Plug those values in, we should get our force. Let's just do that really quickly. Let's try that again. So there we go. So I'm getting 1,714. Make sure you're squaring your radius, because I forgot to do that. And that should be it. So your force is going to be 1,714.84 newtons. And you should be able to know if these are right based on looking at them, because sometimes you get a ridiculous number and it's just like, there's no way. So something to consider when you are approaching these problems. And that's it. Okay, for number 7, we've got a 2,000 kilogram car passing over a bump in a roadway. It follows the arc of a circle of radius 20 meters. So let's draw this. And that is what we're dealing with. So The mass is going to be 2,000 kilograms. And the circle is going to be 20 meters. So the radius of the circle is going to be 20 meters. So you'd write that in there. And we want to know what force does the road exert on the car as the car passes the highest point of the bump. Traveling at 10 meters per second. So velocity is 10 meters per second. But you've just heard that. You've read your problem. So what are we looking for? Normal force, exactly right. So we're going to say normal force. We're going to put a little question mark. How are we going to find normal force? We're going to use Newton's second law. Sum of the forces equals a mass times acceleration. So this is what I have so far. If you've not got that, slow down, pause, make sure you could do this. This is very simple, just setting up the problem, saying what we know, a little bit of mental visualization as well, but nothing overly complicated. So we've got our car at the peak of our hill. We've got two forces acting on it here, no friction or anything, so we've got two forces, right? We've got normal force going up, correct? And we've got weight going down, correct? We're going along a circular path as well. So normal force minus weight, in theory, should equal mass times acceleration. We're going to say circular acceleration, we're going to do v squared over r. And we've run into a similar situation that we had earlier, right? As opposed to a positive centrifugal acceleration, because the accelerator is always going to point towards the center of the circle, we're going to have a negative centrifugal acceleration. So we're going to put negative in front of mv squared over r. The same thing, but now that right side is negative. My right. So, plug in our values, or actually move things around a little bit. Let's make that normal force equals weight minus all of that. So right here, same thing, just moved it around. Or move pieces around rather. We plug in our values. 2,000 times gravity, which is going to be 9.8, minus 2,000 times velocity squared, which is going to be 10, over the radius, which is going to be 20. So let's do that math. So for my normal force, I'm getting 9,600 newtons. And I'll show you that. Let's erase a little bit. So 9,600 newtons. If you've not got that, pause, look at it again. But that is the process. So we've got that. Part B wants us to find the maximum speed the car can have without losing contact with the road as it passes the highest point. So very similar to part B of the roller coaster problem. We want to know what the max speed is. So max speed without the car losing contact. So the car loses contact, it's going to have no normal force. As it approaches that situation, it's going to approach zero, so we're just going to use normal force as 0 here. Normal force is 0. That's just to make sure you've got that. Same Newton's second law type situation. So we've got normal force going up, right? We've got weight going down. Same thing with the mass times acceleration, centrifugal acceleration. V squared over R, all negative, right? And then we don't know the speed. So we can plug in our values. Let me erase a little bit. So 0 as a normal force minus the weight, which is going to be the 2,000 times 9.8, equals negative, let's write some more, negative mass 2,000 times velocity, which we don't know, over R, which is going to be, I believe it was 10. Let's make sure. It's 20 meters. So, got that. And this is our equation. So, got everything set up. We just do a little algebra, and that would be that. Just take your time with the algebra. Make sure you're following every step correctly. 2,000. Let's see. And I'm getting 14 meters per second for our velocity. So 14, if you've got 14, you're doing really well. If not, look back at it, make sure you've got your numbers right, make sure you've got your steps right. But yeah, that exact process. So now we're doing the gravitron problem. This one's sort of tricky, but if you know your chapter 4 concepts, your force diagrams, your forces, Newton's second law, not too tough, not too tricky. It's just a matter of not freaking out. So we've got gravitron, of course. Radius is 3.5, set in the rotation at angular speed of 7 radians per second. The floor drops away, the rider is suspended against the wall in vertical position. We want to know the minimum coefficient of friction between the rider's clothing and the wall. So we know that angular acceleration is going to be 7 radians per second. So omega is going to be 7 radians per second. We also know that the radius of the circle is going to be, or the gravitron rather, is going to be 3.5 meters, right? We've got that. And the floor drops away, and that's it. We want to know what's the coefficient of friction that keeps the person suspended against the wall. So here's what I have drawn so far. Pretty simple. The person drawn, or person against the wall of gravitron, and we've got the radius. Let's draw on our forces, right? So normal force would be the force reacting against the surface, right? So if my back is against the wall of the gravitron, normal force would be going out towards the center of the circle of the gravitron, but it's going to be the opposite, or perpendicular to the surface. So let's draw that. And I guess that's a good drawing. So this is what I've drawn, normal force that way into the center, or just perpendicular to the surface, right? What is holding them up? Friction, right? So we've got friction force going up, which is just going to be mu times normal force. I've drawn that. Friction going straight up. And we've got going straight down weight, correct? So that's what we're dealing with. Excuse me. The idea here is that the normal force is what is causing the centrifugal acceleration. So we could write by that standard, or by that statement, normal force should equal the centrifugal acceleration. So normal force should equal mass times centrifugal acceleration. Centrifugal acceleration is going to be the v squared over r. And I may have ran through that a little quickly, but the idea is we just did a Newton's second law equation. So sum of the forces should equal mass times acceleration. We only got one force causing that centrifugal acceleration. It's normal force. So we're going to say normal force equals centrifugal acceleration, and it's that simple. So I've got that. We also know that friction force is causing us to stay suspended in equilibrium while weight's pulling us down. So in that dimension, we've got sum of the forces equals mass times acceleration. But here we're in equilibrium, correct? So we've got acceleration of 0. Sum of the forces should equal 0, right? Our two forces are friction force, which would be mu times normal force, going up, and we've got weight going down, so minus mass times gravity. So that's what we got. That's what we're dealing with. We want to find the coefficient of friction. So we can just plug in some of our values, but we don't have many values, do we? So we could plug in for normal force. We can plug our normal force into this other equation. So we've got this. We'll just plug that in over there. I may have jumped the gun a little bit with the variables. Instead of the v squared r, because we don't have velocity, we have angular velocity, we could do w squared times r. That would also be on your formula sheet. We're just going to plug in mass times omega squared times r. I said w earlier, but omega squared times r. And that would be the exact same thing, just in terms of angular velocity. So our final equation, let me erase a little bit. Final equation would be mu times mass times omega squared times r minus mg equals 0, but let's move over the mg. So that's equals mg, right? So we're looking at this right there. Do a little algebra, cancel out our masses. So we've got mu times omega squared times r equals gravity, right? We want to solve for mu. We just do gravity over omega squared times r. So I said that was our final equation earlier. I don't know why I misspoke like that, but this is what we're really looking at. So it's the same thing, just rewritten, reworded. But if we got that, we can plug in our values. Let's move up a little bit. So mu equals gravity, which is 9.8, over omega, which is 7 radians per second, squared times r, which is going to be 3.5. Take your time to calculate. If you haven't gotten the answer yet, pause, but I'm getting 0.057 for our coefficient of friction. That's going to be unitless. So if we just got 0.057, I've just done a little algebra. So not too complicated. The main idea here is just to keep track of your Newton's second law problems or equations or concepts, rather. Keep track of your Newton's second law, and it's that simple, really. Like, it's not as complicated as it seems to begin. So that's it. So just a quick look over of what I've seen in chapter 7. Not too complicated. You can do all this stuff. We've got a little bit of the angular movement, angular motion. That's not different from anything you've done in the first few chapters. We touch a little bit of chapter 4 stuff as well. Make sure you keep track of your Newton's second law stuff. Make sure you're drawing your force diagrams. Make sure you're visualizing these things. Make sure you can think through these things. But otherwise not very complicated. The newest thing for you guys would be the gravitational stuff. Make sure you're using your formulas. I don't think it gets too tough outside of your formulas. So if you recognize your variables, you could very well freestyle it, honestly. It's not too complicated. So that's the main thing. Familiarize yourself with your formula sheet for chapter 7. I think you'll be totally fine. And with that being said, that's it for today. Thank you for watching this long video.